Hello, so welcome to the eighth live session for the course Earth Sciences for Civil Engineering Part 1 and 2, which is taught by Professor Javedin Malik from IIT Kanpur and myself Ananya Mukherjee. I am also from IIT Kanpur. I am taking these live sessions. So previously till now we have learned about the components of the earth, minerals, rocks, also the different geological structures that constitute that you observe across the earth. And then we learned about different natural hazards. We learned about different how they change the earth's surface, how they sometimes damage the earth's surface, and the property across the globe. So we have learned about earthquakes, we learned about tsunamis. So today we will be learning about two more natural hazards and how understanding them will help us in preventing them from either happening or kind of minimizing the damage that is caused due to these natural hazards. So the first hazard that we'll be talking about today are landslides. So landslides are nothing but mass movement of rock or debris or earth matter down a slope. So landslides, as the term itself suggests, some particles, some material sliding down a slope. So why is it important for us to understand? Because as you might have heard of various instances, especially in hilly areas or mountainous regions like Himalayas, where landslides are a very pretty common occurrence. So because it destroys the infrastructure over there, it causes damage to life, it causes casualties. So it is important for us to understand how they work, what are the different classifications of landslides, and also the different controls that are influencing the occurrence of landslides. So there are different kind of influences which cause landslides. Some are called internal, while the other ones are called external. So internal influences can range from the slope, angle, or relief. So usually landslides are very common in areas with steep slopes. So gravity acts as a very big factor when landslides occur on these slopes. Also different geological structures or planes of weaknesses like joints and bedding planes, and a lot of weathering processes also cause. Then you have obviously climatic factors such as heavy rainfall and prolonged rainfall. They kind of liquefy the soil around the landslide prone areas, and which causes the earth matter to slide down the slope and cause damage. And how groundwater can affect is when the groundwater is probably mixing with the upper layers of the surfaces, they will liquefy the soil, and as you will see later, it can cause something called a creep, which will eventually lead to loosening up of the material, and it could cause bigger landslides over time. Then obviously inappropriate drainage system, if the water is just let to flow along a slope area, and there would be a much more runoff. And if there are less vegetative cover over there, so the soil is there is nothing holding on to the soil, so that will weaken the that will cause the soil to become saturated with water and saturated with the runoff that we see, and it will get eroded away, and it will also cause landslides. Then there are external influences. Now landslides are accompanied sometimes with bigger deformation processes, bigger ground shaking movements like earthquakes, then forest fires, volcanoes, waves. Earthquakes, as we have studied before also, it will earthquakes occurring against a fault will cause a great ground movement, and due to that movement some area would wherever there is already some weak plains or areas of which are prone to landslides, they will probably slide off the slope. And volcanoes, obviously volcanic eruption again causes a great amount of ground shaking, which will again affect loose soil somewhere or loose material somewhere to slide off. Waves actually kind of erode the base of areas where it weathers over time. So as and when the gap increases or the weathering effect increases, the rock mass on top would topple over. We will see an example of this kind of landslide in the coming slides. Then the most important factor right now recently has been anthropogenic factors, which consist of different the changes that we have in the use of land right now. More agricultural land or more urbanization has led to deforestation, and that kind of loosens the soil. Then there is improper drainage pattern. The water is it easily runs off because of the cemented grounds, and the maximum outflow of water can kind of cause high runoff and then high erosion, and that will eventually cause landslides later on. And also excavation on slopes for buildings, roads, canals, and tunneling. So as this is very much visible in mountainous regions, where due to the cutting along the slopes, because we have to build roads, the upper parts or the roads are very much prone to landslide damage. So now we'll move on to understanding landslides. Now, as I just mentioned that sometimes landslides are caused due to occurrence of a bigger bigger deformation or bigger hazardous event. So the image over here can see that this landslide has been caused due to an earthquake in El Salvador. So you can see that the this entire rock, the soil along with the vegetation, everything has just slid off the slope, and it has destroyed the houses over here. So you can understand that this actually causes a lot of damage to the property, and also a lot of damage to life. That is why it is important to understand landslides. Now, to understand landslides, these are some features about landslide. You can see that these slump blocks. Now these slump blocks will form once this area has already kind of slid down. Okay, so because this material has slid down, the area behind it will kind of subside. They will slowly start sinking. Okay, and then the surface of rupture over here that you see, this is actually the plane along which the weakness had occurred, and this is the area where the landslide actually started from. And because of this surface of rupture, the material on top of this has slid down. Okay, so and you can see that because of such a kind of depression over here, you will get water bodies forming, which is called ponded water. So this is one of the features that is associated with landslides. And obviously there are many other kind of features that are associated with a landslide. You can see that it also forms a scarp, which we had learned before, even in faults, that we can see scarps like this. And then you can see that this is a backward rotated tree. This is one of the signs which can tell us whether landslide will probably take place, or it is a sign or a feature of areas where landslides occur. So you can see that the tree is kind of it is tilting backwards, because the area the roots of the tree are actually moving forwards, as because the movement of the material over is still continuing down the slope. So now we'll learn about the different kinds of landslide movements that we see. Okay, this it can happen due to different kinds of planes of weakness present, or the kind of erosion processes that are taking place over there. So the first one is the flow, that is the descent of material that saturated by water, which makes it heavier, and it can cause debris or mud flow. Now debris is a kind of it consists of a lot of different kinds of sediments, materials. It can have rock, it can have rock blocks, it can have mud, it can have pebbles, cobbles. Okay, and the mud or the soil gets saturated with water, and it starts flowing, as you can see in this area. So over here probably it got this is the surface of rupture, and the material that was over here has slid down. Okay, so this is the flow. Then you have topple. Topple is a forward rotation of material out of a slope. Uh, Over here you can see that there are a lot of joints present here. Okay, so what can happen is due to, say, an earthquake. Okay, so due to earthquake, because of the deformation, because of the ground shaking that has taken place. Okay, so along these planes of weakness also probably some deformation or some kind of movement has taken place, and the rock mass, the rock blocks over here kind of topple down. Okay, so they don't have a planar surface along which they move, they just topple over. Then you have slump. Okay, so slump is just uh, it will not move totally down the slope, it will just from one area it will just get slumped down, and it will just accumulate at say the next area where it is flatter. Okay, then you have fall. Now fall, as I had explained before, how wave action can also cause landslides. So fall is one of the examples that you can see here. Okay, my laser pointer is not moving. Yeah, so you can see the fall over here is that because of the wave action over here, this part keeps getting eroded. Okay, so the top part becomes heavier, and then if there is suppose a joint present over here, so the fall would start occurring over there, and the rock unit above the joint plane would fall down. Then you have creep. Creep is a very slow movement. Okay, it happens over a long period of time, but this is again associated with water saturation of soil. And as you can see, this kind of it keeps happening for a longer period of time. You can see it in the tilt of the poles or tilt of the trees. Okay, so this can happen. So this is called a creep, and you will see that the front part of the material that is creeping below, it will form lobes kind of structure. Okay, so because of the friction that is below. Okay, and then the next one you have is the slide. Now the slide is that there will be a plane on top of which the material is going to slide down. We will see now that there are different kinds of these landslide movements also. This this diagram kind of explains how much what is the kind of speed of the different landslide movements. So you can see the rate of movement of creep is very slow, that is 1 millimeter per year probably. Okay, then you have the slide, that is the landslide. So that will also happen slowly. It will happen probably the material, the surface of rupture is kind of developing over the year. Then you have earth flow or mud flow. This is partly rapid, as we saw in the image before. the kind of landslide that happened with an earthquake. So probably the area, the soil over there is already saturated with water, and due to ground shaking, or the kind of traveling of the waves that are generated by the earthquake, the ground shaking. So then you will have an earth flow or mud flow depending on the kind of material that is there. And debris or avalanche and flow are also like very rapid. This can just happen, all of a sudden, and this kind of causes a lot of damage too, and it is very difficult to kind of predict it beforehand. Now there are a few classifications. So as you can see, for falls, okay, over here you can see that there is a rock fall, then there is a debris fall, and this is the earth fall. Okay, so these are the type of movements that are given on the left hand side, and the top one will tell you the different kind of material that we are observing at that area. So suppose you have a fall, and you can see over here that there is a scar, and I think this is supposed to be the area where the plane of weakness had taken place, and the material over here loosened up and it fell. Then there is debris. As I said, debris is a mixture of a lot of things, so this will fall down. Then you have the earth fall. Okay, so this will again, this you can see as this is a forming kind of another lobe kind of a structure. That is because of the the material that is present. Then you have topple, so you have rock topple, debris topple, and earth topple. Again, you can see it is along these vertical kind of planes of weaknesses. Then you have slides, so you have rotational, and then you have translational. Okay, so the rotational one over here, that the surface of rupture is kind of a convex plane. So it will the top part is kind of it will slump down. Okay, because of the loosening of the material along this failure surface. And then again, this is the this is rock, so and then this is the debris, and then this is earth. Okay, so the earth, you can see, is that it will kind of form uh, successive rotational slides. All this will not go down together. Okay, because obviously the material over here can kind of sustain the the weakness planes over here because of the material. But you can see that there are successive rotational slides. Suppose this kind of material first go for slumps down till here, then along with this area again it will slump down here, so you will have a successive rotational slides. Then translation is that there is one planar kind of failure surface, and there is not much rotational movement that is there, or there is no backward tilting also that is kind of observed when we are talking about rotational slides. Then we have spreads. So spreads happens that when sudden horizontal movement, yeah. So when sudden horizontal movement happens on very gentle terrain, you can see that the slope isn't very steep over here. Okay, so this can happen, the lateral spreads because of liquefaction of the soil over there. It can happen. Okay, so the soil is probably liquefied, or due to an earthquake there is liquefaction of soil. We had learnt about this liquefaction of soil in earthquakes in the previous sessions. So it can happen suddenly because the soil is either previously liquefied or the earthquake has caused liquefaction, and this can also happen on very gentle slopes. So again, rocks and debris, this is mostly rock underneath and debris are on top, and then you can also have that with earth kind of material. Then you have flows. Okay, so you have debris flow, you have earth flow or mud flow, and this on rock, it's usually the weathered product that is present on top of the rock can cause the flow of that. Then this is the debris flow, where you can see that different areas, probably looser material is falling down together and then forming a bigger they are joining together and causing flow of the material downwards. Then you have earth flow. This is also this is already probably wet enough material, and that is why this can happen kind of quickly when there is kind of ground shaking here, or the removal of vegetative cover, or due to excavation. This can also happen. Then complex landslides are those where you can have two different movements together. So suppose you have rotational plus you have slump, you have kind of debris flow along with something else. Over here, as you can see the example, there is slump earth flow with rockfall debris. Okay, then you have non-circular part of rotational, like there is some part that is rotational, okay, some part that is planar. Okay, so that can also come under complex landslides. Now we learned about the different types of landslides, the movements, and how you can classify these landslides based on their movements. Now we need to understand how we can control these or either probably prevent landslides by controlling the movement of the material and stabilizing the material. Okay, so you can see that the first one would be removal of unstable materials. Okay, so suppose you have, this is your slip surface. Okay, so if you remove the this material over here, so you can see that the driving force of the material is kind of reduced, and there is an increased stability over here. So this was the slip surface and this is the ground surface. So we removed the material over here, so then the driving force of this material is reduced. Okay, now there is another way we can do it, that remove material from the lower part of the surface. If we do this, this will reduce the stability, because still there is a lot of material that is still existing above the slip surface, and this can very easily move downwards and cause damage if suppose you have any infrastructure over here. Now this is the effect of the water table and the kind of landslides. You can see that if the water table is much below the ground surface, okay, it does not intersect the ground surface, then there will be increased stability, because the interaction will be less. There will obviously be interaction, but it will be less. So this is a much stable kind of this will be a much stable condition. But if the water table is rising, okay, as we had talked about how groundwater can also influence the occurrence of landslides. So you can see that over here, if it meets the ground surface, so the pore surface will pore pressure will reduce the resisting force, and this will reduce the stability of this area when it comes to landslides. Now how we can kind of stabilize our the earth material around our infrastructures, to kind of control and prevent landslides from happening. So these are some of the examples of how you can construct some features which will prevent it. So you have lightweight fills. Okay, so this is your capping, you are putting gravel on top, and this is the till, and suppose this is the slope that was being affected. So you have kind of created these benches with gravel and different material, also wood fiber. Okay, so you are kind of preventing from this part or from sliding down the slope. Okay, then you have earth building buttresses or counterweight fills. You can see that these are the buttresses that have been created, so to prevent from this area from sliding down this entire place and kind of causing damage. You can see that these are kind of the buttresses that are built. These are bigger rock blocks, and then they are confined, or they are placed with a concrete lining outside. Then you have surface drainage control. Surface drainage control, this helps us when there is runoff from heavy rainfall, okay, or suppose you have insufficiently built drainage systems for the residential areas somewhere around this area. So what this drain that is present over here, this will collect the surface runoff, and it will kind of take it down to a place which is take it down to suppose any of the stream or rivers that is nearby, okay. So the this part, okay, that is closer to the road is not affected by the surface runoff from here. You can see over here that this is the gravel backfilled trench, and this is like this is the outlet where the water will flow away, and this is your road suppose, okay. So this is the unstable slope. So without the surface runoff kind of affecting this unstable slope, we can still stabilize this. Then you have subsurface drainage, okay. So you can build pipes. This is the failure surface, okay. So so as to reduce the interaction between subsurface water and liquefaction of soil, okay. So you can create such drain pipes. Again, this will kind of stop affecting the slope over here, okay. You can see this material is very loose, so if this gets liquefied from underneath near the failure surface, this can very easily cause failure and kind of damage this entire area. So this is one of the other ways where you can kind of stabilize the slope. Then you have retaining walls. This is kind of timber, wood timber used to retain, to kind of obstruct these slopes from, or these material to flow further below. You can see over here in this schematic also that this is how you would create walls which will prevent this loose material from coming down the slope. Then you have earth stabilization and reinforcement, okay. So suppose you have steel grips, okay, and then there are you put bedrock put rock blocks over here to prevent the movement from the slope over here, okay. So this material will probably be it's probably excavated first, and then these steel strips are put over here to kind of prevent further material from coming down. Then you can also have wire mesh that is filled with different kinds of rock boulders, okay. So that will again prevent this loose sediments or the loose material from here to flow down. You can also have wire mesh confinement. This is very much visible when you go to Western Ghats, along the mountains, along the range over there. You can see wire mesh confinement next to the roads that are built through the Western Ghats. So this will kind of prevent bigger rock blocks from just toppling over. The wire mesh will catch those rock blocks and minimize the damage to the infrastructure over here. Now the next one is much more sustainable, that is vegetative cover. As you can see that there are the grass is being grown, and first you kind of make these step like features, and you put grass over here. So these grass will hold on to the material around this area, and then it will obviously prevent the further sliding of the material over here. Now this is a slope stability classification, okay, and this is kind of with respect to India, the landslide the hazard map probably. So very high hazard, you can see actually most of these are limited to the mountain regions that are present. So you can see, as I was talking, the Western Ghats, this is very prone to very high rainfall. So most of the landslides occur here during monsoons, and even similarly in the Himalayan region, and then also in the northeast region, okay. And then you have different six classes. Okay, these are based on the kind of the frequency of the landslides that happen, and also the slope angle that is present, and also the material, like whether the scars or the scarps that are developed, whether they are very fresh or they are well defined. So uh, in class 1 you will, if you have fresh, that is very recurrent landslides over here. So these scars that are seen as features of the landslides are very fresh, and they are very well defined, because these are the areas where the landslide movements happen very much often. So according to that, there are six classes. Now we come to the next natural hazard, that is floods. Floods is very common on the Indian subcontinent, and these are some of the most common causes. That is obviously climate related, also due to kind of urbanization, human interference. Okay, so most of them are usually climate dependent, like heavy rains, overflowing rivers due to kind of heavy rains, or increase in discharge of in the river. Then obviously one of the human influence would be broken dams, the dams that we built, suppose they have a failure. Then you have ill planned drainage basins from the urban areas. Then again disaster oriented, like storm surges and then tsunamis. Then obviously another human influence would be lack of vegetation. Then the melting of snow and ice, this is happening very much in the recent time, where due to the massive glaciers being melting very fast. So the again the inflow of the water in rivers is increasing, and it is causing you know it is causing floods in the lower areas, also due to migration of the river course, as we see for in example of the Kosi river. So we see Bihar is very much affected by that. Even from Brahmaputra, it is kind of similar ways how it is affected. So now we'll learn river dynamics. So this would be a very simple, kind of a river system. Okay, so the source is somewhere in the glaciers, probably because of the melting of the glaciers. We have the source of the river from there. Then these two are tributaries. Tributaries join together to make the main river channel. Okay, then this is the confluence. Confluence is where the two tributaries meet. Okay, for example, for Ganga we have Alaknanda and Bhagirathi. Okay, so they are kind of tributaries joining together to making to make Ganga. And then also Yamuna is a part of it. Then the river will flow. Okay, so this area is the source. Okay, so this is the youth stage of the river. Okay, this is the source area. Then these are the flood plains. Okay, so these are kind of you will have medium flow over here. It will kind of the rate of flow is moderate over here. Okay, and then in the later part where you have the delta, the movement or the rate of flow is very slow, and most of the bigger depositional features that we see, like delta, happens near the mouth of the river. Okay, and over here when you say upstream and downstream, so the upstream would be this area and downstream would be this area. So you can see that the discharge in the river system increases downstream. Okay, because more and more tributaries would be joining the river channel, increasing the discharge in the river. Then the channel width also increases downstream. Then the channel depth also increases with downstream, in the downstream area. Then the average velocity, it increases downstream when it is flowing along slope areas, but over here the velocity kind of decreases. And the quantity of load, the sediment load, okay, it can have pebbles, cobbles, and then mostly smaller sediments like sand and silt. Okay, so the quantity of sand and silt is kind of very high in this area. And the load particle size, as I said, sand and silt would be more in this area of the river system, and since they are finer particle size, you can see that the load particle size also decreases downstream. Then the channel bed roughness also decreases because the erosive power of the river in the first two stages is much more than what it has in the mouth stage. And also the slope angle or the gradient of the channel bed, the river channel bed, also decreases as it goes downstream. Now we come to river geomorphology. Now the river geomorphology, also called fluvial geomorphology, is due to the action of the different sediments that are carried by the river, starting from the source all the way up to the delta. Okay. So most of the erosion happens in the first, in the the source part of the river system, and also the mid part of the river system, as I had explained before also. So you can see that these sediments, okay, these finer sediments would be suspended in the river channel unless and until the velocity of it reduces reduces enough so that these suspended sediments would get deposited, and these bigger kind of sediments, say pebbles, cobbles, gravel, they will be kind of flowing along the bed, the river bed, and they will be causing most of the erosion that takes place. Okay. So the different kinds of erosion, the processes is abrasion, then you have attrition. Okay, and due to these abrasion, you can see that kind of these you can say fractures are formed in the riverbeds, and further abrasion will kind of deepen the channel bed along these fractures, and also hydraulic action also happens along these fractures. You can see that due to this traction, saltation, abrasion, the river kind of forms these very sharp V valleys. Okay, then you have this spur is kind of not entirely formed valleys. Okay, so those are called spurs, and then these are the river banks. You can see that this is the kind of the load that you can see over here is mostly present in the the river bed, and this is what is causing the erosion over here and formation of such valleys in the youth stage of the river. Now you can see that this is the source area. Okay, so this is where your lakes, glaciers and rapids are there. There is also precipitation, which is causing the which is kind of um, which is a source for the river. Then you have the transition zone. In the transition zone, you can see that there are more tributaries coming and joining the main channel over here, and these are called floodplains, where you see that when there is an increase in the discharge of the in the river. Okay, so these areas would get flooded, and when the flood when the water starts receding, okay, so the suspended load that we have seen before will start getting deposited in these areas. Then these are the flood plain zone. Okay, so this is a starting of the flood plains, then you get into the flood plain zone. Now the flood plain zone, the the steepness, or I should say the slope of the land is very less. Okay, so and also the velocity of the river is very low, so it will not exactly cut through the land over here, but it will start creating what is called meanders. Okay, so it will start flowing along the easy path, the areas which is easier for the river to cut, even while maintaining the velocity that it currently has. Okay, so due to that you will have oxbow lake, then you have salt marshes, and finally it will form deltas, and it will also deposit the other sediments that are present over here. Now we come to river channel patterns. As you can see in the right hand side figure, you know, there are different kind of classifications of the channel patterns. First we learn about the number of channels. So there is single, then there is wandering, there is braided, and there is anatomosing. Okay, so this single one happens at the youth stage, or near the source of the river. Okay, then slowly it starts kind of branching out when it reaches much lower at the slope. Okay, then this braided pattern is very much seen in the plain areas, in the floodplain areas. And this anatomosing that you can see is, it happens nearby the deltaic regions. Okay, and the what governs these different kind of channel patterns is obviously the velocity of the river. Okay, and then you have degree of sinuosity. A straight channel would, it would be created nearer to the source, where the velocity is so high, it will just, just cut across that one plane of weakness and it will flow. Then low sinuosity would happen at a lower velocity place, and sinuous would take place in floodplains and next to the deltaic regions. This is kind of what we see in meandering river streams. And you can have different kind of sinuosity, regular, irregular, tortuous. Okay, and in the left hand you can see that if we take a cross section, okay, along the river channel, okay, you can see that the flow of the water, this is the flow of the water. Okay, so that would be, the top part would be flowing faster because the load, the sediment load in the lower parts of the water would, kind of do the erosive action. Okay, so this is A. Okay, so this is where, this channel is kind of straight. Okay, so this is the river bed is also kind of, in a symmetrical fashion. But when if you take a cross section, along a meandering portion of the river, you can see that the outer part, okay, so the the concave part of this area, it would be faster. Okay, because of the, the turn that is over here, the water will flow faster over here, and the erosion also takes place much more on this part of the meander, while the inner or the, the concave part of this meandering stream, you can see that this yellow part is actually the deposited sediment. Okay, so this is where the deposition happens and this is where the erosion happens. This is a very simplistic channel pattern that we that is given over here. So then you can see that, according to the particle size and the flow velocity, different areas can be demarcated. Okay, so when the flow velocity is low, and these the heavier particles would get kind of deposited. Okay, then when the this part, okay, when there are smaller particles, okay, and even with, lower flow velocity to much higher flow velocity, these particles would get transported with the water. Okay, and the particles that are eroded, that's why when I said the erosion mostly takes place when the flow velocity is very much higher, and this happens in the, the youth stage of the river, where the flow velocity is much higher. And this is what happens when the flooding in the flood plains happen. Okay, so this is bank full. Okay, and then flood could happen either due to increase in discharge, or kind of sudden increase in rainfall. Okay, so you can see that the first the area that is, the first sediments that would get deposited are the coarser material, and as the water moves towards the outer parts of the river bank, you can see that the finer sediments would also get deposited. As I had said, the these particles would get deposited at a much lower this flow velocity. You can see that over here, since the water will start moving much slowly as it moves away from the banks, the finer and thinner sediments would be deposited on the floodplain. And these areas, okay, this area that is formed due to the coarse sediment deposits, these are called levees, natural levees, okay. So these get built upon, okay, due to repetitive flooding. So these are some of the erosion and the deposition kind of uh, features that are associated with rivers. Then when you come to say meandering, okay, so you can see that this is meandering, okay. This is the area of the fastest current. As I said, the outer part would get this will get eroded because of the in faster flow velocity of the river. This part would get deposited. As you can see that this is the deposition, okay, this area would get deposited, and this is the erosion, okay. So suppose, as I had mentioned, this is suppose the this is how the river is at the first stage, okay. This is a okay. Then with with time, this will become more and more sinuous, okay. So the sorry, I'll just draw this, okay. So you can see the sinuosity will increase, okay. And as sinuosity would increase, okay, so the flow velocity will kind of start decreasing, because it has to maintain the equilibrium also. So then what happens is, when it becomes too sinuous, okay, okay, so slowly what happens, as you can see that this part becomes very much thin, okay. This part will also become thin, okay. It cannot erode anymore, it cannot deposit anymore. So what will happen is, this area would get cut off, okay, and the river will automatically join this one, will join this meander, and then it will start flowing like this, okay. And this part that is cut off will form what is called an oxbow lake. So this is very much common in places where it was first meandering, and then this area would get cut off from the main river channel, and it will form an oxbow lake. This is also one of the features of fluvial geomorphology. Then the next thing that we come are alluvial fans and deltas, okay. Yeah. So you can see the alluvial fan forms at the foothill of the slopes, okay, and deltas form at the interface between the land and the sea or lake or ocean, okay. So this happens at the last stage of the river, and this happens where the slope kind of suddenly decreases, and we move to the low gradient valley floor or low gradient plain areas, okay. And this is where more of the distributary channels will then start forming from the main channel that was coming, okay. Now we come to drainage morphometry. Why this is important for us to know is that we need to understand how dense the drainage of the entire river basin is, okay. And it will then help us to understand how prone this area is for flooding due to the flowing of the rivers over there. So you can say that this is a very low density drainage. How? That because the number of streams, okay, of different orders are different, okay. So the smallest streams are given the lowest order, okay, and the main stream that is there, the main channel that is there, okay, that is given a higher order. So you can see that there is first 1 and 2 and 3, okay. So this is a third order river system or drainage system, okay. Over here you can see that there are numerous smallest order streams that you can see over here, and then where they join together and form a bigger stream, that is the next higher order, that is second, then there is third, then there is fourth, and fifth is the main river channel. Okay, so this is a fifth order drainage pattern. So using these you can actually calculate the bifurcation ratio. Okay, so this will tell us how much branching has taken place and what is the measure of the the drainage density of that river basin or the watershed area. Okay, so usually it's more than one. Okay, and this is the formula. So suppose you're given kind of this drainage pattern, suppose. Okay, and you are asked tell the bifurcation ratio between the first order streams and second order streams. So then we have to kind of take the particular order. Suppose we have to understand the bifurcation ratio of the first order streams. So you will take number of streams of first order and divided by total number of streams of the second order. This would give you the bifurcation ratio between the first order streams and with respect to the second order streams. And similarly you can also calculate the drainage density. That would be the the ratio between the total length of streams. Okay, so what you do is you calculate the length of streams of each of the order. Okay, suppose the it will differ obviously. These can be calculated on different kind of softwares, and you can also calculate this manually if you have kind of traced out the drainage pattern or with the help of a map, and then you can measure it. And with respect to the entire area that the drainage the basin is drainage basin is covering. This is kind of how a drainage evolution happens. Okay, so as I said, in youth stage you will have more straighter streams. Okay, and also the bifurcation ratio is much lower, and the order of and these are also lower order of drainage basins. Then with that you can see that bifurcation ratio kind of increase. You can see that the smaller order of streams kind of generate from the main channel itself. Okay, so there is less amount of branching as such. In mature stage you can see that the branching increases, smaller order streams also increase in number. Okay, and then you have maximum extension. Okay, and then you have integration and channel loss, sometimes capture. This is where suppose how we explained oxbow lake. Okay, maybe the velocity of the river or the discharge in the river kind of decreases. Okay, so some of the channels would be lost, especially the smaller order channels. Okay, and sometimes that capture means that suppose these two branches that you can see, these kind of come together. Some of these lower order streams would get defunct, they won't be working anymore, and they will be lost, or this major channel will kind of capture this channel, and then together they will become one this kind of a branch. Okay, where the smaller order streams have now reduced in number. So this is how drainage evolution can take place, from the youth stage to the mature stage to the maximum extension that happens. Now we'll see about different drainage patterns. Okay, so these drainage patterns are kind of they are influenced by the geology over there, the lithology over there, the structures that are found. For example, in dendritic pattern. Okay, in dendritic pattern you can see this is common in flat lying areas. Okay, and massive homogeneous kind of massive rocks. I mean as in the rock type that is present is kind of uniform. Then you have parallel, which usually happens along sloping surfaces, and this again happens in homogeneous kind of rock units over there. Now radial and annular, these are very much kind of related to domes and dome structures. Like radial happens near volcanic eruptions, and then annular happens either this can be a dome in between or this can be a basin over here. Then you have trellis. Okay, so trellis is these happens in, suppose there is very intensely folded sedimentary terrain over here. Okay, so the planes between two folds, okay, they will act as planes of weaknesses, and the rivers will start flowing along those folded regions. Then rectangular is very much governed by the existence of fractures and joints and massive rocks. Okay, so this can be seen in such areas. Now we come to flood intensity. Okay, so the flood intensity, this is a very useful graph to understand the the flooding pattern characteristic of of one of one river basin. So you can see that as rainfall is happening, so the kind of flow discharge within the river kind of increases. Okay, it reaches a maximum, and then at after a certain time this will start decreasing. Okay, so discharge will start decreasing. Okay, and this flood hydrograph is sometimes influenced by different factors. Over here you can see that the drainage basin shape kind of influences. If there is this kind of a drainage basin shape, you can see that the peak happens in this area. Okay, whereas for this kind of basin shape, we see that the peak has moved towards the narrower drainage basin area. Now over here, since this is kind of it has a broader it has broader drainage areas along the two end points. Okay, so this area and this area, both of them will show that there is a double peak over here. Now you can see that the drainage density also kind of affects the hydrograph. Okay, so the peak discharge is more and high drainage density areas than low drainage density areas, and similarly you can see that how vegetation also controls the hydrograph. Okay, you can see that if there is more vegetation, the flood hydrograph is not the peak flow discharge that is plotted over here is not much. Okay, so the discharge kind of decreases with increasing vegetation. You can also calculate the channel, sorry, this is not density, this is the discharge, and this is wrongly written. I will correct it in the notes. Okay, so the Q is channel discharge, and it depends on the width of the channel, the depth of the channel, and the velocity of the water flowing. Okay, so this is how you also calculate the channel discharge in a river. Now we come to flood mitigation. We learned about the different drainage basin patterns, the kind of different stages of the river system. Okay, so that gives us an idea about how you can how understanding these factors which are influencing the channel discharge, the river discharge, and we can try to minimize the risk, minimize the damage that is caused by the flood due to floods. So for flood management, we have three kind of areas that we can work on. The first one is hard engineering. So hard engineering would mostly contain creating of flood relief channels and spillways around areas which are inhabited by population. Okay, so the flooding flooding of the river, you can channel the water, the flood water, to drainage systems and spillways, and it can either flow back into the river at some areas, or it can be utilized in a different way. Then you have straightening and channelization of river. So where the river channels are artificially widened, so it can hold more water when there is an increase in the discharge. Then you have building dams. Obviously we know how dams help in kind of blocking the downstream flow of the river. So if the channel discharge increases, you can close the dam gates and you can hold the water, and you can release them as per the as per the convenience, so as to not to flood the downstream area. Then you can, as we talked about natural levees, okay, so you can kind of, build upon these natural levees artificially, or you can create embankments next to the river channels, okay, so you can hold the excess water due to increase in river discharge, okay. And then also you have something called flood walls. Now these flood walls are, kind of not waterproof, and they are not very sturdy, but they can also be constructed. Then next we have is soft engineering. So in soft engineering, first we, kind of do zone mapping of floodplains. As you can see in the lower part, we have, we can classify in 4 zones with respect to the kind of features that are associated with the river channels. Okay, so and you can also have, you can increase the floodplain area so that the river is, naturally allowed to flood that area, and it can create its own kind of habitats over there, create its own kind of vegetation, which will, help in preventing further damage due to flooding of the river. Then you have restoration and afforestation. Okay, so you increase the vegetative cover, and you can obviously it is more sustainable to do it in this way, and also obviously the process would be slow, but it would help eventually, to even constrain the river channel from, deviating from its course. Then you have administrative measures, that is mostly, kind of involving warning systems, and also, kind of how information is passed from the say the agencies which are creating these warnings to the community which would be affected. Okay, so this is some ways that you can mitigate the damage caused by floods. Now we come to groundwater. Okay, so the groundwater is important for us to know while, in civil engineering perspective, is that, how deep is the water table, what kind of, material, what kind of aquifer is already there, if it's going to affect or contaminate the groundwater around that area. All these things are necessary for us to understand, sorry, all these things are necessary for us to study so that we can make an informed choice regarding, building infrastructure at such places. So you can see in this diagram, you have zone of aeration, you have water table, you have zone of saturation. Okay, so the zone of aeration is kind of moist top layer of the soil, but it is not fully saturated with water. Okay, so this can also be called the unsaturated zone. Okay, and then beneath this is, your water table and your saturated zone. Okay, suppose you kind of drill a well to kind of extract the groundwater in this area, as most of the housings do have this. So this place, there is a kind of a disequilibrium between the the water that is the water that is being extracted and the level of the groundwater that is there. So you can, kind of form a cone of depression in such areas. Okay, and this would be called the water table. This is the average depth or average level of the groundwater that is present in an area. Okay, so you can see that this area is, as I said, this is would be a moist area, but the this can also hold the not hold exactly, this can transport water. Okay, so suppose this area is, being affected by rainfall, so whatever surface water is being, accumulated over here, it will start slowly infiltrating and percolating downwards, okay, through this porous and permeable soil, and it will reach suppose say the zone of saturation. Okay, in later on in the coming slide, we will learn the different kind of geological formations which help in, kind of holding such groundwater. And when we talk about those geological formations, we would be using two terms, that is porous and permeable. Porous means that there are spaces between the grains forming the rocks. Okay, and permeable means that these voids are connected to each other. Okay, so a material can be porous, but it can be impermeable. Okay, so the porous means that it has the spaces to hold the water, but the water cannot transmit from one area to the other. So then it would be called an impermeable rock or impermeable material. Okay, so over here, as we can see, there are different types of aquifers. Okay, so aquifer is any geological formation that can hold the groundwater. Okay, so over here you can see that this is the water table. Okay, so unconfined aquifer means there is no top layer, which is kind of preventing this aquifer from interacting with the water table and the kind of material on top of the water table. Okay, now you can see that this is an confined aquifer. Okay, both these aquifers will be formed in high porosity and high permeable material, for example a sandstone. Okay, so unconfined, that there is nothing that is kind of restricting the movement and interaction with the top surface. And over here you can see clay. Okay, so clay is essentially a porous material, but it has lower permeability. Okay, so that is why this is confining this groundwater area. That is why this would be a confined aquifer. Over here you can see that these layers, okay, these layers can be called aquitards. Okay, aquitards. So these are what? These are clay, silt, sand. Okay, these are porous, but these are not permeable. Okay, now aquiclude is this has high porosity and low permeability. Okay, so aquiclude also can contain water, but as it has low permeability, it cannot transmit. Okay, so this can also be something that will confine the water from moving downwards. Okay, then another kind of geological formation that we have is aquifuge. Aquifuge is it has very low porosity, it has very low permeability. Usually igneous and metamorphic rocks are something that are that can be called aquifuge. So the water over here cannot seep down anymore. Okay, it cannot percolate below this aquifuge. So these are kind of the geological formations that are associated with different kinds of aquifers, and how they kind of form the groundwater system below. Now this is kind of an easy table for you to understand how aquifer, aquitards and aquiclude and aquifuge are what is the capacity of water storage, permeability, yield of water, and also examples of the geological units or rocks which form these different kinds of aquifers. Now, why is it important for us to understand groundwater and the different kind of geological formations? Is because the amount of time that the groundwater takes to move, okay, starting from starting of seeping down towards from the top surface to the lower surfaces. Okay, and excuse me, if we do not conserve groundwater, we run a risk of extracting too much and depleting our water table. So as you can see that the top layer, okay, the unconfined aquifer, where I think most of us kind of target these aquifers for our daily needs. Okay, so these would get recharged and discharged within days and years. Okay, but if we talk about a much deeper confined aquifer, okay, so for water to kind of recharge these kind of aquifers is going to take very long. You can see it takes centuries and millennia. Okay, so but if we keep pumping and if we keep extracting such deeper aquifers, okay, recharging these would take a longer time, and kind of in unhindered extraction or excessive extraction for all our purposes, daily purposes, or infrastructure building or whatever. So this, if we start extracting more of these deeper aquifers, we run the risk of depleting this, and this won't get recharged very fast. Okay. Also, these deeper confined aquifers are kind of, they have less contaminated water compared to unconfined aquifer, because of the, firstly because it's much more closer to the earth's surface. Okay. So all pollutants and contaminants are very easily, seep through, because there is no confining layer. Now when we say confining bed, as we talked about, say aquitard. Okay. Suppose this is an aquitard, suppose this is sand plus clay. Okay. So these layers, these confining beds can actually filter those contaminants out, and that is why these deeper confined aquifers could be, purer than the unconfined aquifers. But again, if we start extracting more of these confined aquifers, and if we, start excavating more and more at deeper depths, and we reduce the amount of such confining beds, so the filtering that happens due to the existence of these beds will, again reduce, and it will contaminate the deeper confined aquifers also. That is why we need to understand the the water table, how the groundwater is recharging over there, what are the sources for it, recharging. And also, while building, we have to understand how groundwater can affect the foundation of our infrastructures. Okay, these things are very necessary, and for that we have to know the basics, and also, understand how the groundwater at a particular area is working over there. So that's it. So this is the end of the live sessions. So if I will float a Google form on the, from the discussion forum itself, and if most people agree, then we could have a revision session this coming Thursday from around the same time, 6 to 7 p.m. Okay. So the form would have whether you are interested to have it or not, and also if yes, what are your doubts. So it will help me to create either the content, or I can prepare myself, according to some of the questions or queries or doubts that you would have. So I will float the form by tonight, and these live sessions are ending today for this course. I would like to thank you for attending this course and these live sessions, and I hope that it has helped you all, and I hope it has helped you in solving the assignments, or even get a good summary of the week's content that is already taught by Javed sir. So